Alright, so in the last video we talked about the magnitude and direction notation for vectors. And so now we're going to talk about the notation that is going to be most useful for us, which is called unit vector notation. Okay, and before we talk about that, I really want to focus on why it's even important. So the reason we have to use unit vector notation is because it allows us to take this two-dimensional vector and turn it into basically like two separate one-dimensional vectors. Because basically we're going to go through this whole chapter on two-dimensional motion, and it's really just doing one-dimensional motion twice. Because all the tools that we have for analyzing motion only work with one dimension. And so when we have a vector that's in two dimensions, we can only look at it as if it was in one dimension. So we have to look at it's like two dimensions separately. Okay? And so I'm going to kind of show you some ways that you could kind of think about it to understand what's going on. And then we'll go ahead and talk through like some of the math behind it. So let's look at this vector right here. Let's pretend that this is some object that's kind of going in two dimensions here. And let's say that there's a person right here that's looking at that object. Okay, kind of perpendicular to it here. Okay, when they look at it, they're not going to see it as this long. They're going to see it as about this long. Okay, because from this angle, that's the longest it's going to look. Okay, and so they're kind of limited by this angle. Okay, well, a person standing right here is going to have a similar experience, except to them it's going to look a little bit shorter. Okay, it's going to look something like this. Okay, now they're both looking at the same thing, but they're seeing it as a slightly different size. Okay, and these are called like projections. So if we were to take this vector and project it onto the x-axis, that's what we see. If we were to take this vector and project it on the y-axis, this is what we'd see. Okay, if we know what this is and know what this is, if we say like what the projection for x is and the projection for y is, that's another way of describing that exact same vector. Okay, and so that's why we use this unit vector. That's basically what unit vector notation is going to do for us. Okay, but on this same problem, let's say that this is displacement, and let's say though instead of displacement this is a velocity vector. So something is going to travel this distance in some amount of time. Okay, so let's say it's moving like 5 meters per second. Okay, well, to this person, it's going to take them the same amount of time to get there, but this person, it looks like they're going a little bit shorter distance. So if this is 5 meters and it takes them 1 second to get there, this person still sees them take 1 second to get there, but maybe instead of, to them, it doesn't look like 5 meters, maybe it just looks like 4 meters. So instead, maybe they're going like 4 meters per second. Okay, and then over here, you have the same issue going on for this person. They see it taking 1 second to get from here to here, but instead of going 5 meters to them, it maybe only looks like they're going like 3 meters. So maybe they're going like 3 meters per second. Okay, and so the name for these projections are called components. And so we have this horizontal component and this vertical component for this vector, okay, that are basically what the person down here sees and what the person up here sees. And if we put those two together, we basically get like a right triangle. The thing with vectors, you can slide them around. So we can slide this one over to here, and it's like 3 meters per second. And so we can see here that if we take these two component vectors, they're going to bring us back to this original vector we started with. Okay, and the way that we get there is using just Pythagorean Theorem. We have two sides of a right triangle. A squared plus b squared equals c squared. Okay, so it's a little bit of vector, just kind of like switching between the two types of vectors. And so now we'll get into like a little bit more about unit vectors. Okay. Okay, so with unit vectors, it's the same thing. Okay, but we basically have to kind of find a way to write it out. And so I'm going to kind of walk you through that process. So let's say this vector is 12 meters long, has an angle of 30 degrees, okay? And so we want to find what it looks like for this person right here, and what it looks like for this person right here that are standing and watching, okay? And so you might remember that the way that we're doing this is by taking this and turning it into like the sides of a right triangle, okay, those projections. And so the way we'd find this one, if this is a right triangle, this would be the adjacent side to the angle, and so we use cosine. So cosine of 30, that angle, is equal to the adjacent side, which is what we're missing, in this case x, over the hypotenuse of 12 meters. Okay, now what happens is, when we solve this, we multiply the 12 over, so we get 12 cos 30, and when we do this operation, what's happening is we're literally taking this vector and we're projecting it onto the x-axis. So it's called a projection because if we were to take a light and shine it on it, that projection would be the shadow of the vector on this axis, okay? And we're going to do the same thing for the y component, okay? But instead it would be this vertical piece right here, the opposite side, and so we use sine. So sine of 30 is equal to y over 12 meters. We multiply the 12 meters over, so y equals 12 meters times sine of 30. And it's the same thing here. Okay, we're multiplying. We're basically saying if you were to shine a light this way, the shadow that appears on the y-axis would be the projection of this vector onto the y-axis. Okay, and so that's what we get when we multiply the hypotenuse times sine of 30. Okay, and so we'll go ahead and just plug those in real quick. So for x, we get about 10.4 meters. Okay, and then for y, sine of 30 is 1/2, so we get about 6 meters. So we're saying that if this vector is 12 meters, has an angle here of 30, it's 30 degrees north of east, okay? This component here is 10.4 meters. This component here is 6 meters, okay? And let's call this vector A. Well, if we're going to write vector A in what we're going to call unit vector notation, we would basically write these out. So the x is 10.4 meters, and the y is 6 meters, okay? But we have a problem, and this is going to be the fundamental challenge that's going to really cause some of those problems in this unit, okay? All the physics that we do can only happen in one dimension, okay? And we run into problems when we try to combine quantities that are in separate dimensions. Okay, this quantity here is horizontal. Okay, this quantity here is vertical. I can't combine these quantities, and if I do, I'm going to end up with something bigger than I started with, right? 10 and 6 is 16. I only started with 12. So I have to have a way to indicate which direction these things are. And so what I use is quantities called unit vectors that basically represent one length along each axis. So one length along the x-axis is called I, okay? So this is 10.4 meters times I, and then one unit of length on the y-axis would be j. If we were in 3 dimensions here, one unit of length, and the third dimension would be along the direction k. Alright, and so now these aren't like terms. We can't combine an I with a j because they're not like terms. Okay? A couple other things in vector notation. The way that I indicate that A is a vector is by putting an arrow over it. Okay, and there's a special notation for unit vectors. Instead of an arrow, it's a little like hat. Okay, so this would be I hat and j hat. Okay, and so then we have now taken vector A and written it here in unit vector notation. Okay, so here we have vector B. Okay, and vector B is actually a velocity vector. So we have a velocity here of 10 meters per second at an angle of 40 degrees, that is to the south of west. So vector B, if we write magnitude direction notation, is 10 meters per second, 40 degrees south of west. Okay, but I want to write vector B in unit vector notation, just like we showed with vector A. So that means we've got to break it, make it as a right triangle, break it into its components, write it as an I and a J. Okay, so go ahead, and I want you to do this one yourself. Write vector B in unit vector notation. Okay. Okay, so to find that horizontal component, the I component, you would multiply 10 by cosine of 40 to get that horizontal projection. For the Y component, we'd multiply the 10 meters per second times sine of 40 to get that vertical projection. Okay, and here we have vector B. All right, well actually not quite, okay, because there's something wrong with this. So I'm going to show you why. When I go to draw this vector out, okay, what I'm going to see is that it tells me to go positive 7.7. Well, positive x is going to be kind of this way. And so positive 7.7, okay, and then positive 6.4, well, this is in the wrong quadrant, okay, and it's actually in the opposite direction. Okay, and so I have to have a way of showing that it's going to the left and it's going down instead of to the right and up. Okay, so this I component, if this way is positive, then this way would be negative, so that would be a negative 7.7. Okay, and then since this is up and that's down, this is going to be a negative 6.4 meters per second. Okay, so there we have vector B in unit vector notation. Alright, the last thing I'm going to show you is if we do have a vector in unit vector notation, I'm going to show you how to go ahead and take it back to magnitude direction notation. Okay, so here we have vector C, which is an acceleration vector, and it's happening with 4 meters per second squared in the I direction and negative 2 meters per second squared in the J direction. Okay, and I wanted to turn this vector into magnitude direction notation. Well, the first thing I'm going to do, I'm going to sketch it. So I have positive 4, okay, I have negative 2 for J, okay, and so then I want to find the magnitude of this vector. So the way I do that is using the Pythagorean Theorem. Okay, now once we draw this as downward, we don't have to make it negative anymore, the negative just to show that it's going down. So the magnitude is, we just use Pythagorean Theorem, the square roots of 4 meters per second squared plus 2 meters per second squared, okay, or the square root of 16 plus 4, so the square root of 20. Okay, alright, and so we get about the magnitude of about 4.47 meters per second squared. Okay, and so that's the magnitude of this vector. So vector C is 4.47 meters per second squared. We also have to find the direction. We need this angle. Okay, and so if this is a right triangle, this would be the opposite side. That's the adjacent side. So tangent of that angle is equal to 2 over 4, or 1/2. So that would mean that theta is equal to the inverse tangent of 1/2, which is about 26.6 degrees. Okay, so that's going to be 26.6 degrees, and this is to the south of east. And so notice that whenever I'm going to draw these, I'm going to start with the horizontal one first, and then the vertical one, and so we're always going to be measuring away from east or away from west.